Okay, and we'll also talk about the squeeze theorem. All right, so look at this example. Okay, from last time we should be able to do one like that. All right, what do we need to do in order to, well, first off, I guess I should go back. What happens when you plug 0 in? 0 in the denominator, and you also get 0 in the numerator. Okay, but the big problem is the 0 in the denominator. All right, so what can we do to algebraically manipulate this in order for us to actually find the limit? Multiply by the conjugate. So we multiply by the square root of x plus 2 plus the square root of 2 in both the numerator and the denominator. All right, so when you multiply the two binomials up top, you end up getting the inside or the radicand of the first radical, the x plus 2. All right, minus the radicand of the second radical, which gives me 2. And on the denominator, you have x times that square root of x plus 2 plus the square root of 2. All right, and then you notice that the plus 2 and the minus 2, those cancel out to 0. All right, if you can imagine that those are gone, you look at the numerator and you have an x. In the denominator, you also have a factor of x, so those x's would actually cancel out as well. And so that ends up giving you the limit as x approaches 0 of 1 over say again?
I said it becomes 2 on the bottom.
Yeah.
So you see this.
Square root of 2, x plus square root of 2 plus the square root of 2. Right? And can we now substitute the 0 in? We can, because there's no longer a 0. The denominator is no longer 0. And so when we do that, we end up getting 1 over the square root of 2 plus the square root of 2, which you could put that together as 1 over 2 square roots of 2, which is totally fine as an answer. Or if you wanted to rationalize it, that would give me the square root of 2 over 4. If you multiply by the square root of 2 in the numerator and denominator in order to not have a radical on the bottom. Yes?
Our answer can't be the limit of x approaches 0 1 over the square root of x plus 2. I guess I have to sorry.
You're saying this one? The first one?
The one above it. Like the 1 over the square root of x plus 2 plus the square root of 2. Yeah, so like the limit, that equation can't be our answer, can it?
No, the answer needs to be a number for limits.
Yeah.
Yes.
But we can't like set it equal to the answer because that's not the original equation, right?
You mean I can't set it equal to?
Because that's not the original equation, so if we're like writing out our answer, we have to rewrite the original equation as equal to the limit of that is equal to this.
I mean, if you have an equal sign and limits all the way down, you're fine.
Okay.
Yeah. You have a problem if that limit notation, which I know is horrible to write out every time. If you don't have that, that's when there's a problem. If you have that limit notation, you're good. All right, any questions? All right, if you look at your bottom slide there are a few more rules there. We kind of use the trig ones in our homework. All right, the basically says most functions, okay, if not all functions, if the number is actually in the domain, you can just plug it in. Okay, that direct substitution works for limits. as long as it exists. All right, you have your sine, your cosine, your exponential, your logarithms. Again, as long as what you're plugging in there is bigger than 0, because that's in the domain of natural log or all logs, which we might have to talk about. And then your inverse trig functions as well. Okay, and just side note, notation-wise, this is the inverse sine function. Okay, it means, hey, and we'll see that here in a second. You also might see it written as arc sine of x. Okay, either one of those, they're the same thing, it's just different notation. Anytime you see that inverse next to a trig function, you could have also written it as arc that trig function. All right, so let's look at this example. All right, this theorem says I can plug the 0 in direct substitution, okay, as long as what's inside there is actually in the domain of the inverse trig function. And the domain of the inverse trig function, or the inverse sine, is between -1 and 1. So if I plug 0 in, I get the, I don't have a limit anymore because I'm plugging it in. I have the inverse sine of 0 plus 1 over 2, so I get the inverse sine of 1/2. And so now I'm just trying to figure out, all right, what angle or what radian value has a sine of 1/2? Anybody remember? 5 or 6. Yeah. 5 or 6. All right, that's, again, the hand trick could come in handy there, no pun intended. Okay, since I'm looking for 1/2, I need to figure, all right, what angle when I put down the finger gives me a 1 on the bottom, because the sine is on the bottom, and that's my ring finger. And so my ring finger is pi over 6, so I know that's the answer. All right, kind of going backwards there. All right.
Should it have also been like 5 over 6?
I'm glad you brought that up. Okay, I was going to bring that up. For this to be a function, okay, for the inverse sine to actually be a function, we limit where we're looking at it. Okay, so when we're looking for answers, I guess if we wanted to talk about the range of the inverse trig functions, all right, the range of arc sine or inverse sine is going to be just between -pi over 2 and pi over 2. All right, the range for arc cosine is going to be between 0 and pi. All right, and then for arc tangent, its range is only going to go, well, it's going to go from -pi over 2, not including the -pi over 2, to +pi over 2. All right, and the reasoning for that, if you care, which apparently, what happened? Oh, I messed up. All right, because if you think about sine, all right, that's the sine function. All right, now, what the inverse function does is it switches the x's and y's. Okay, if you remember finding inverse functions. And so if I were to switch the x's and y's, I would set x is equal to the sine of y. All right, I've now got this green curve. All right, but the problem with this green curve is that it is not a function. Okay, it doesn't pass the vertical line test. All right, so I have to just narrow down where I'm looking at it. Okay, and so we narrow it down from negative pi over 2 to positive pi over 2. All right, because if we can narrow it down to there, we have something that's a function. Because if I go any further, up to 5 pi over 6, okay, this would start to go back on top of itself. If I were to go down further, it would start to go back on top of itself. Okay, so we do restrict that domain. All right, that's why if I were to just to write y is equal to arc sine of x, they would just draw that part. Okay, and then cosine, arc cosine, goes from 0 to pi. Okay, and again, I can't, if I were to go below 0, it would start to go back on top of itself. So that's why it's not the same range. All right, and then arc tangent, all right, looks like that. And so it just, I mean, because we're looking at it only from one little thing of tangent, so if we did, see what happens we did there. Y is equal to tangent. This is what tangent looks like, if you remember. So if you were to switch those up, you would get that business going on. Okay, but I definitely don't want all of those, so if I just look at just this part in the middle, okay, negative pi over 2 to pi over 2. Okay. Where did you go? Did I? Well, there we go. All right, now the next couple of examples. All right, next couple of examples. If I were to substitute 0 in. All right, we would get 0 times the cotangent of 0. All right, and if we remember what the cotangent of 0 is, all right, that's actually undefined. Okay? Cotangent does not exist at 0. Cotangent, the easiest way to think about it is that cotangent is equal to cosine over sine. And since it's at 0, sine is 0, that would make me have a 0 on the denominator, and so it doesn't exist. All right, so we got 0 times does not exist. Well, what is that? Is that 0? Is it does not exist? What is that? I'm unsure. Okay, this is another one of those indeterminate forms. Okay, I can't tell just by plugging this in. Okay, because the whole limit property of just being able to plug in the number to two things that are multiplied by each other only works if both of them actually exist. Okay, so this one doesn't work. Okay, we're gonna have to figure out a different way. Okay, we'll come back to it. All right, same thing is gonna be true here. If I were to substitute 0 into cosecant, all right, or cosecant squared, since cosecant is equal to 1 over what?
What are you doing with sine?
1 over sine. And since again at 0 sine is 0, cosecant is undefined there. Okay? So again I've got a case of I got 0 squared times does not exist squared. Okay, so I've just raised my problem to another power. Okay? Still can't be done directly. Okay, so there's got to be another way. I mean, I'm not sure exactly how to do it algebraically. Okay, I can break cosecant into 1 over sine, but right now I don't have anywhere to go with that. All right, and so that's why we need this next theorem, okay, and some of the consequences of it. All right, the squeeze theorem. All right, what the squeeze theorem says is if I've got some function that I cannot find the limit of as x approaches a certain number. Okay, so I got this pink function. All right, if I can find a function that's always beneath it, except for possibly at that point, so always beneath it or at the same place as that function, except for possibly at that point, and I can find another function that I can put on top of it, always, into that little region, except for possibly at that point. If I can find a top, bottom, and a top, and I also know that the limit of the bottom part at that point is the same as the limit of the top part of that point, then I know that the limit of the function that I can't find the limit of, it has to be the same number. Okay? We're squeezing it in, or we're sandwiching that in. Okay? Historically, there's also, I think in Italy, I don't know the Italian for it, but it's basically translated to English as the two policemen and a drunk theorem. All right, because if there is a unruly person, okay, but that's benign, but you're trying to corral them through a doorway. If I get one person on one side, one person on the other side, if I can keep that unruly person in between them, those two people, all right, as I get towards the doorway, the only place that unruly person can do is do what? Go through the doorway. Okay, if I put one on one side, one on the other. Now, I'm going to show you one example of how we can use the squeeze theorem, how we would do it. If I want to find the limit of x squared times the sine of 1 over x. Okay, I want to prove that it's 0. All right, well, notice if I throw 0 in, I get 1 over 0, which is undefined. So there's a problem there. Okay? So this is what I can do. All right, I know that, what do I know about sine? What does sine always, what does the sine graph look like normally? Up and down and up and down and up and down, all right? What's the lowest it ever goes? -1, right? And the highest it ever goes is +1. True, yes, that inequality is true. All right, now if we replace that theta, okay, since that's true for any theta, any angle that's true, if I replace that with 1 over x, since sine is always between -1 and 1, no matter what that theta is, whatever that angle is, okay, then this is also true. We good with that? All right, and then for inequalities, if I multiply the same positive number all the way through, that inequality is still going to be true. If I multiply it by 5 all the way through, I don't have a problem with my inequality, do I? All right, so what I'm going to do is I'm going to multiply all terms by x squared. So times x squared times x squared times x squared. And so that gets me negative x squared is less than or equal to the x squared times the sine of 1 over x, which is the function I was trying to find the limit of. Is less than or equal to positive x squared. So I've essentially sandwiched in or squeezed in this function I'm trying to find the limit of. All right? And the reason why that's nice is because if I take the limit of negative x squared as x approaches 0, can I do that one? I can direct substitute in that to that one, yes? That's equal to what? 0. And I can take the limit of the top function, x squared, as x approaches 0. That's also going to be what? 0. All right, since I have my functions squeezed in between the bottom and the top, and I know that both of those functions have exactly the same limit, and that limit is 0, by squeeze theorem, I know that the limit of x squared times the sine of 1 over x is also equal to 0.
What happens when they're not equal?
Say again?
Will there be a problem when they're not equal?
Well, if they're not equal, then you can't apply squeeze theorem, so I'm not sure. Okay, and that's where actually doing squeeze theorem, saying, hey, use squeeze theorem to find that, is a little difficult because you gotta get creative on how you're finding the functions that go around it. Okay, and so I really won't ask you to do that. I'm going to have a couple examples in a second where questions I could ask you. Okay, because for years and years, squeeze theorem was in the AP curriculum, but it was never on the test. Until like 2 years ago, all of a sudden there was a question that you had to apply squeeze theorem. Okay, and I'll show you how that question was kind of asked. All right, I think that's actually up next. All right, this is the type of question I could ask you about squeeze theorem. All right, let G and H be functions defined by, and I give you a function for G. I give you a function for H. All right, if F is some function that satisfies that F is between G and H for all X, can I find the limit of that F of X, which I know nothing about besides the fact that it's between G and H, as X approaches 1? All right, and if so, what is it? All right, so notice how this is set up to do squeeze theorem. I've got my function is in between two other functions. Yes? All right, so that would, if you saw that, you say, oh, that's probably going to be that squeeze theorem that Mr. Wilbanks talked about on September the 24th. All right, and so what I would do here is say, all right, well, I know that F is between G and H. All right, so let's find the limit as X approaches 1 of the G function. All right, so the G function, which is up here, can I plug in 1 to that? Yep. That would be negative 1 plus 2 plus 2, so that's 3. And I would find the limit of the h of x function as x approaches 1. That would be 1/2 minus 1 plus 7/2 when I plug the 1 in. Which also gives me what? 3. All right. So you could say, yes, the limit of f of x as x approaches 1 is also equal to 3 by squeeze theorem. All right, so basically if you see that, hey, I know a function's in between two other ones, can I find out what its limit is? Plug it into both of the bottom and top. If they're the same thing, then I know what it is. If they're not the same thing, then I can't determine it by just using that. All right, I think that's what we have down here. All right, again, I've got f is between g and h in this region from 0 to 4 around the number I'm looking the limit of. Can I find the limit of f? All right, so for the g of x, if I say what's the limit as x approaches 2 of that g of x, which is the cosine of x minus 2 plus 2. All right, 2 minus 2 would be 0, so the cosine of 0 plus 2. Cosine of 0 is 1. And so that gives me 3. All right, if I look at it, h of x, the limit of this ugly thing. One half x to the third minus 1/2 x squared minus 9/2 x plus 11. All right, if I plug 2 in, 2 to the third would be 8, half of 8 would be 4. 2 squared is 4, half of 4 would be 2. 9/2 of 2 would be 9. We get our plus 11. So that ends up giving me what? 4. All right, and so since these are not the same, okay, we know that the limit of f of x as x approaches 2 cannot be determined. At least by squeeze theorem. Those two have to be the same.
Does it mean that the limit doesn't exist, or it just find it?
It just means maybe those two functions were bad functions. Let me find two other functions that would also do the same thing, but they're the same. There's just basically not enough information. All right. Do I want to talk about this? All right. Squeeze theorem is also used to prove this. Okay, I'm not going to go into the details. Okay, if you want to look up, it's actually kind of nice, but it took me about 30 minutes to do it in the BC class the other day. Okay, just to prove something we're just going to use. Okay, so just know we've seen this limit before. We saw this when we did with numbers, and we saw it when we did it with graphs. All right, and squeeze theorem is actually what we use to prove this. Okay, something to do with areas of triangles and sectors and triangles. Okay, we can back our way into the squeeze theorem, and so basically what happens is we have this graph right here. Our pink one is the sine of theta over theta, and we could squeeze it in between cosine and 1 to prove that it's actually 1. All right, but we can use that. All right, we could use that actually to prove the problems we skipped just a few minutes ago. All right, so let's look at this example here, the sine of 4h over h. If I want to find the limit of that as h approaches 0. Almost done here. All right, well, from the previous page, I knew that if this was theta and this was theta, that answer is 1. Unfortunately, the argument of the sine up top is not the same as the denominator, is it? Okay? Our whole goal here is to make the denominator exactly the same as the inside of the sine. So guess what? We're just going to make it that way. All right? I'm going to rewrite this as the limit as h approaches 0 of the sine of 4h. All right, and I'm just going to go ahead and, you know what? I want there to be a 4 on the bottom. All right, because if the denominator and the inside of the sine are the same thing, I know that whole thing is 1. All right, but if I put a 4 on the bottom, I've changed the value of my expression. So I counteract that by multiplying by a 4 in front or a 4 on top. Because essentially I've just multiplied by 1. And so when we do that, then we know that, hey, the limit of 4 is 4, and the limit of this part is 1, and so my answer is going to be 4. Okay, so when you see these problems, the goal is to get the denominator to look exactly like what's inside the sine, and then you'll have your answer. So on this one, I want there to be a 5 on the bottom. So what I need to multiply 3 by in order to make it turn into 5. Five thirds? So if I multiply by 5/3, that would turn that denominator into 5. But if I multiply by 5/3 on top, in order to basically, I'm saying 1 on top, 1 on bottom. Then we end up having 5/3, because that 5/3, the first one, can come out. And then we'd have the sine of 5h over 5h. And according to what we just learned, that's equal to 1. Okay, you probably can see some shortcuts there too. All right, but that's the reason why why those work.
Yeah.
Say it again.
Do we not multiply by 5/3 to find the limit? Because the first one, we also multiplied by 4.
Do we not multiply by 5/3?
Is it, because it says equal to 1, doesn't it equal to 1 times 5?
So here, this 5/3, yeah, I wrote it differently there. I brought the 5/3 out, but it's the same.
That was just one of those rules that we learned, right?
One more
Just one of those rules that we learned, right?
Yeah. If you have that 5/3, I could leave it underneath inside there. I mean, I could have at this point right here said, hey, this is 5, and so I know that this whole thing is 1 and my answer is 5/3.
Okay.
But the answer's
That's
5/3.
fine. What?
I'm confused. The answer's 5/3 or 1?
So many 5/3 are.
Oh. You should have said, hey, Mr. Wilbanks, your answer is wrong. And then I've been like, oh, okay, I get you. Yeah, my answer is 5/3.
Okay, I was so confused.
Somebody say, hey, Mr. Wilbanks, your answer is wrong.
Well, I don't know if it's wrong or not. I have no idea.
I'm sorry. I was thinking there was a problem with my process, not the fact that I wrote the wrong number down. Fail for the day. Does that make sense now?
More.
More? We'll do another one.
Yes.
Minimization approaches 0 of sine of 6x over I'll make it 13x. Bless you. Anybody see the like total shortcut on ones like that?
We don't get the multiple compound.
Say again?
They go get the multiple compound.
Yeah. Well,
We guess that's the
yeah.
I thought that was too easy. I thought we just worked out.
Yeah. I mean, it's going to end up that because I mean, how do you get the denominator to be the same thing as the inside? You multiply by the numerator, what's inside the thing, by the denominator of that. Okay, and that's going to be your answer.
What happens to the sign?
The 5?
The sign is the sign just go away.
Well, I mean, because you end up having, when you multiply by the 6 over 13, all right, this becomes 6x on the bottom. And so this whole thing right here, and the reason why it works is because this is the sine of something over the same something. And that whole box there turns into 1. And then you just also have this random 6/13 out there. And that's why it's 6/13 times the 1.
Even if it's like 11x on the bottom, it still just turns into 1.
I mean, this is no longer 11. This is not 13x on the bottom. It's what?
6.
This is just going to turn into 6x because you multiply by the 6 over 13 to transform that 13 into 6 so that it matched up with this up here.
Is that the same thing for like cosine or anything else?
Yeah. Let's look at this one. All right, so if I wanted to find this limit, all right, this is actually going to use some trig. All right, what you know, we might catch that one tomorrow. I can tell y'all are gone. All right, so we're gonna look at those last two. We'll save those for next time. There are, or for your homework, finish up that worksheet. Okay, anything you don't know, can't work over, we will cover. All right, And then if you'll also, I believe, let me double check that I put it on there. There's also going to be a delta math exercise. Okay? All right, and so it's limits analytically. You can either go straight to delta math if you write this down and know what's going on. Or again, if you look at my Canvas page, Unit 1, the latest thing is going to be down here, 1.4. All right, there's a delta math, and then complete that worksheet. All right?
Can I go to the restroom?
Yeah.